we'll take derivatives of both sides of this equation with respect to x. So you take the derivative with respect to x of ln of y. Okay, and so you use the chain rule on this. This would be 1 over y dy dx. Again, using the chain rule. And then the derivative of all of this. Well, what's the derivative of all of this? It's a derivative of a sum and a difference. So you can split up the derivatives into 3 derivatives here. And the derivative of ln of x squared plus 1, well, that's ln of u, right? So that's u prime over u. So what's u prime? The derivative of x squared plus 1 is 2x, so that's u prime. So you've got 2x over u, right? X squared plus 1. And then you've got plus 1/2, and then u prime is 1 over u. X plus 3, and then minus u prime, that's 1 over u, right? 1 over x minus 1. Okay? Now, all you have to do is use a little bit of algebra and solve for dy dx, because that's what we're interested in. So you multiply both sides by y. So you've got dy dx equals y times all of that up there, right? You can see that. I'm not going to write that all in. Blah, blah, blah. All right? So it's y times all of this. Well, what's y? Y is this. So if you want to be complete, you put this instead of y, and there's your derivative. Okay, so on complicated rational functions, logarithmic differentiation seems to work quite well. All right. Now, if u is a non-zero differentiable function, the antiderivative of 1 over u du is equal to ln of absolute value of u plus c. All right. So we already know that the integral of u to the n du is u to the n plus 1 over n plus 1 plus a constant. That's provided n does not equal 1. We've seen this rule before. And you may have wondered, well, what if n equals 1? Well, now you know. If n equals 1, then it's ln of absolute value of whatever this function is, this denominator. And you take absolute value to make sure that you're not taking the ln of something less than 0. Of course, u is not going to equal 0 here, because then if it did, this would be undefined, the 1 over u. Alright, so if u happens to be negative, this makes sure that this is going to be ln of something positive. Alright? So for example, let's take a look at a definite integral from 0 to 2 of 2x over x squared minus 5 with respect to x dx. Okay? So I'll do a u substitution on this one. We're going to let u equal x squared minus 5. And then du is 2x dx. And then let's change the limits of integration using u here. U of 0, the lower limit, is equal to, well, x squared minus 5, or 0 squared minus 5, which is minus 5. And then the upper limit, u of 2, is 2 squared minus 5, which is negative 1. So now our new integral is integral from negative 5 to minus 1 du over u. And that equals ln absolute value of u evaluated from -5 to -1. And this is equal to ln of absolute value of -1 minus ln absolute value of -5. Note that you do need absolute values here, because if these were just negatives, then the ln's would be undefined. And so this is ln1 minus ln5. Well, ln1 is 0, so that's just negative ln5, and that's your answer. Alright, now don't give me a decimal approximation. It's better to leave it like this, unless you're working in a practical application, but we're going to assume you're not. Alright, I'm going to cover one more example here for you. Let's take the integral from negative pi over 2 to pi over 2 of 4 cosine theta over 3 plus 2 sine theta d theta. So we'll do a u substitution again. Let u equal 3 plus 2 sine theta. Then du is equal to 2 cosine theta d theta. And we don't have 2 cosine theta, we have 4 cosine theta d theta up here. So we need to multiply that by 2 on both sides. So you get 2 du is equal to 4 cosine theta d theta. And so now the u covers the denominator, and the 2 du covers the numerator of the original integrand. Alright? And now, one more step, we need to change the limits of integration. These limits were with respect to x. We've changed variables here to u, so we have to change the limits with respect to u now. And so u of negative pi over 2, well, what's u? It's 3 plus 2 sine theta, so that's 3 plus 2 sine of negative pi over 2, where theta equals negative pi over 2. And that's equal to 3 minus 2 sine pi over 2, using a little trig there. And that's equal to 3 minus 2, because sine pi over 2 is 1. So now we have 1 as our lower limit, and then the upper limit is u of pi over 2, which is, again, 3 plus 2 sine pi over 2, which is 3 plus 2 this time, and that's 5. So now we have the definite integral from 1 to 5 of 2 du over u, and you can write it like, oops, too many equals here. You can write it like this: 2 times the integral of 1 to 5 from 1 to 5 of du over u, and that's equal to 2 ln absolute value of u evaluated from 1 to 5, and in this case you don't really need the absolute value bars, so that's 2 ln 5 minus 2 ln 1. Ln 1 is 0, of course, so this is just 2 ln 5, and that's the way you should leave your answer. Alright? Okay, now there are also, on page 464 in your book, integrals, or rather tables for integrating the tangent and the cotangent, and I want you to read that on page 464. There are also some more examples. Memorize the integrals or the antiderivatives of tangent and cotangent there in the table, and they do give an explanation for those. I want you to read those. Also look at example 8 on page 465. Alright, let me give you a homework assignment on this. That would be section 6.2 again. And the homework will be 5 to 37, every other odd, page 47, or rather problem 47, and then 51 to 67, every other odd. Okay, well that covers this section. Enjoy.